Okay, so this is the second problem. Once again, I'm not going to read it. This is 2015 question 4. And when I see these tables, I'm going, you know what, multiple tables, this might be a chi-squared, but I'm not sure. And then I read on, it says, use the sample data for the customers to conduct a statistical test. So at least I know I'm not working with basic probabilities, says the stat test, to determine whether the waiting time of the new branch are inconsistent with the acceptable probabilities for the waiting time categories. So when I look at this, I have multiple categories. And the fact that I have multiple categories to compare means I can't be working with the proportion. So if I'm not working with the proportion and I have categories, this is the chi-squared. So what type of chi-squared is it? Well, when I look at this, I have counted data. When I look at this, I don't have counted data. Because this is not counted data, I only have one column. If I have one column or if I have one row, this is a goodness of fit. So this is a goodness of fit. And I have 1, 2, 3, 4, 5 categories. So 5 minus 1, my degrees of freedom are going to be 4. Now, they tell us up here that we have 100 customers. So my expected value on all of these are going to be times 100. So real quickly, I'm going to enter this data into my calculator. And I've already entered the customers, and the customers go into L1. Right, so these are the customer counts, and that should sum to 100. This is 0.3, 0.25, 0.2, 0.15, and 0.1. Now, I just go up to the top of L2, so second 2 times 100. Obviously, I could have done it by hand if I wanted to. So I need to write these down. There's my expected values, 30, 25, 20, 15, and 10, all right? And they didn't give, if it's in red, they didn't give it to me. Okay, so what they asked me to do, the distribution of actual wait times is consistent, because we always like to start with equal. So is consistent and then is not, okay, with the acceptable wait time proportions. Conditions, random sample. They told us that. They said they had a random sample of 100 customers, so that's a given. We need to check the Goldilocks. All right, and here we go. Not too big. 100 divided by 0.1, reasonable to assume that the bank has more than 1,000 customers, therefore N is less than 10% of the population. The next one has to be big enough. Big enough is greater than 5. So I need to calculate those expected values. Well, I did, and all of them were greater than 5. We said it was the chi-square goodness of fit test, so we're going to go second quit. I'll go stat, test, and this is chi-squared GOF. Oops. All right. My observed is an L1. That my expected is an L2. Be careful. They will not put your degrees of freedom in there. Mine happens to be in there, but it's not. It normally isn't. So 1, 2, 3, 4, 5. So 5 minus 1. Calculate. And I get a chi-squared of 4.09. So 25, that was my observed, minus my expected, divided by my expected. I can do plus dot, 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 and then do the last one. And I end up getting 4.09, all right? And I ended up getting a p-value of 0.393 or 394, something along those lines. Contributions. Unlike the independence test, the goodness of fit will calculate the contribution. So there they are. And we see a 1, and this is the largest contribution. So this is the one that's most different from what was expected. But with a 0.394 p-value, it's going to be greater than any alpha, so we're going to fail to reject. So our p-value is 0.394. We failed to reject the null. There is not sufficient evidence at alpha equal 0.05 to suggest that the distribution of actual customer wait times is not consistent with the bank's acceptable wait times. So in other words, the wait times appear to be consistent, all right? Or we can't say that they're not consistent, all right? So we have to, we are basically, we can't prove the null, or we can't prove the null either, but we cannot reject the null, all right? So that takes care of that one.